determine our S. Okay, so what's so unique about this problem is you have to rely on the shear flow design on this. Okay, then you can visualize better. Or not, you say, oh no, I have one on the left, one on the right. Are they related? Okay, if you don't design the shear flow, it can be pretty bad, or you cannot visualize properly. Now I'm going to do something further with this. Okay, I'm going to formulate the shear stress distribution equation for this. Okay, so let's look at this. So we're going to I'm going to take this diagram. Okay, and I want you to see something. Okay, so I'm now this is extra. Okay, and I think it's good that you know this. We are going to determine the shear stress distribution equation. Okay, we're going to determine the shear stress distribution equation from here. Okay, so now on the what? On the flange and major web. Okay, so we know, I'm going to sketch this diagram again. Let's look at the flange first. Right, so let's consider the flange first. Okay, let's consider the flange. So if we were to draw a transformation, this is Y and this is Z. Okay, so the flange will start from here, or we will start from here first. Right, we'll start from here first. And if we were to design the shear flow, it will look like this. And then we know that it will, over here is a junction. And for the junction, it will come down. Okay. So the flange, right? If you look at this distribution, right, you will distribute from left, okay, from here, left to right. Okay. It can be right to or left to center, or you can formulate the function from right to the center. Is also the answer will the equation be slightly different, okay, but the trend will be the same. Okay, so when that's the case, you will start from, so the left, you will know that the first moment of area is low. The center, the first moment of area will be the highest in the flange. Okay, so Q, so it's related to Q low to Q high. So when that's the case, we are going to formulate, so we're going to call this 0, okay, and then this will be moving towards the right. The function will be a function of Z. Okay, so the Z direction is low, where the Z direction or the Z variable will start from the low Q to high Q value. Q means your first moment of area. Okay. So let's look at this. So Q as a function of Z, or Q about the Z axis as a function of Z, right? So because this is our X, this is our Y, this is our Z, okay? So this will be equal to the minor flange. So QZ of the minor, web, plus by QZ as a function of Z on the flange. Okay. So this over here is a constant, right? Because the shear flow has to distribute on the entire member. Okay. And then the flange is a variable. Okay. So the Q flange of the minor web. So the width is 1, the depth is 3, the Y bar is, I can't remember now, 3.3548. 3.3548. And then minus by 3 divided by 2. Okay, then plus. Okay. So the width over here is a variable, right? The width is a variable, so it's Z, right? So from low is 0, so this is Z. And then the depth, we know the depth is what? The depth is 0.5. No, the depth is 1. And then the Y bar, right? The Y bar is 3.3548 minus by what? Minus by 1/2. Okay. So when you calculate this, so 3.3548 minus by 3/2 times 3 times 1, so it's 5.5644. Then you plus 3.3548 minus by 0.5 times 1, so it's 2.8548 Z. Okay. And then you calculate the shear stress distribution, right? So the limits is from 0, Z, until where? Until the halfway, right? Until the halfway of the 10, until 10 divided by 2 inches. Because the left and the right is symmetry, yes or no? Right? Based on thin wall analysis, right? Like the distribution here and the distribution there, right? So the function is the same. Okay, the function is the same. So what the function will be the same in this aspect. So that's why it's only up to halfway. Okay, because at the center is where both meet, at the junction. Okay, this is a junction, not a terminal. Okay, it's the junction. So from here, you know that the shear stress as a function of Z is equal to V. So we know that V is equal to 700 divided by I. Our I is 337.43. The thickness, right? Thickness is perpendicular to the shear flow, which is 1. And then is this function over here, 5.564 plus by 2.8548 as a function of as a variable Z. So this is equal to 700 times by 5.564 divided by 337.43 divided by 1 is 11.543. Let me do it again. 700 times by 5.564, 337.43 divided by 1, 11.543 plus 700 times by 2.8548 2.548 divided by 337.43 divided by 1, 2.8548 is equal to 5.922 or 5.922 Z. Okay, so let me do it again. 9.543, correct. 5.922. Okay, so what does this mean? Okay, so if I were to now consider the right, we have this. So over here, our shear stress is equal to 11. Okay, so our draw up to here, up to here. So this is 0. This is 5 inch. Okay, this one is 5 inch. And this is our 10, 20, 30. This is our shear stress. And if we look at the function, is a linear function. So over here, you will have 11.543. And then at 5, so 5.922 times 5 plus 11.5, 11.543 is 41. So 40 and 50. So 41 is somewhere around here, right? So this is 41.153. Right, so it's a straight line. Yeah, better draw a straight line with a ruler. Right, so this is how the distribution look like on the what? On the flange. Okay, right? Okay. So now that's why the limit. So on the other side, how does it look? If I'm going to sketch on the other side will look, or on the right hand side will look exactly the same. What I'll do is I'm going to point here. I'm going to Control C, V, and I'm going to rotate. It's going to look the other direction. Okay, so this is how the shear force will distribute. Again, if you look at the right, so if you want to consider the right hand side, you have to be cautious, because over here, if you consider right hand side, over here is where Z is equal to 0, right? Because remember, the Z direction, the variable Z will start from low Q, because Q is low over here. And for both sides, Q is high over here. Okay. Right. So this is for the flange. On the web, right? I think you all can visualize this now. It's not going to be a linear function. Okay, it's going to be a second order polynomial function. So let's consider the web, right? So again, Q as a function on the z-axis as a function of z will be equal to Q of the minor web plus by Q of the flange plus by the Q as a function of z for the major web. Okay, so now you have to be very, very cautious. Okay, you have to be really, really careful now. Okay, I'll tell you why. So Q web and Q flange, we have calculated that before, and it is equal to 39, right? 39.677. So this is equal to 39.677. Let me check again. 39.677. So what we are considering now, right? right? So this part and this part are constant. This is also constant. Now we are considering the what? The wet.